All right, hello. My name is Tate Niekamp, and this is Physics 2 Lab 5. So, jumping into the introduction, the purpose of this lab is to showcase both Faraday's law and Lenz's law by inducing a magnetic current as well as a magnetic field through the use of a cylinder composed of aluminum foil to effect acceleration. So, basically, we will drop a magnet through an aluminum foil tube and explore the result. The result being how fast it takes the magnet to fall through the tube. So some physics principles in this lab are Faraday's law, Lenz's law, the Biot-Savart law, Newton's second law, and Newton's third law. So the main result is that the average time to drop experimentally was about 3.7 seconds, and the time to drop computationally in GlowScript was about 3.85 seconds. So the experiment. So the system is the bar magnet and the roll of aluminum. The surroundings is the Earth. We basically dropped a magnet through an aluminum tube and recorded the time it took to fall. We did this 5 times to find an average. Then we did this on GlowScript computationally. So some assumptions and data in the lab. We ignored air resistance experimentally. The length of the tube was 28 centimeters. The width of the tube was 1.5 centimeters. The inner tube radius was about 1.25 centimeters. The average time to drop was about 3.736 seconds. The magnet mass was about 0.023 kilograms. And the magnetic dipole moment from lab 3 was about 1.2734 newton meters times Tesla to the negative 1. So some sources of error. So possible sources of error could come from inaccuracies in the measurement of the tube, as well as inaccuracies in the measurement of the time it took for the bar magnet to fall. So here's my GlowScript code. We're going to go through this for a little bit. In the beginning, we're initializing the graph, explaining the constants, and creating the aluminum foil. Then we create the bar magnet down here. Then we create the magnetic field of the bar magnet. Then we calculate the magnetic flux. Then we start simulating the loop. This step 7 is the gravitational force on the magnet. Then we start calculating the current in each ring on the tube. Then we find the typical B field at each ring. Then we find the net magnetic force. And then update the magnet's velocity and position as time goes on. So if we were to run this code, it would look something like this, with the bar falling from the top down to the bottom, the bar magnet. And here is the velocity versus time curve. So the first question here in this interpretation is basically which way of the current is red, which way is blue. So the computational model is red. Therefore, red must be counterclockwise, with blue being clockwise. This is based on the fact that the induced current must be in the counterclockwise direction because the North Pole was facing downwards. What happens to the dynamics of the system if you flip the magnet? The dynamics of the system if the magnet was flipped would cause the induced current to flip directions. However, the flux is going to be the same. The change of flux will be the same. Therefore, motion would be the same. How does the total time in tube of your real world system compare to that of your computational system? So it was very, very close, within maybe two tenths of a second. But the computational model is likely more accurate, as it does not suffer from any form of human error. But the computational model does not account for air resistance, and if it did so, it would be more accurate. What does the shape of the velocity versus time plot tell you about the forces? So there's basically that it reaches terminal velocity. In the beginning, the velocity is slowing as it enters the tube. Then it is constant, where the net force is 0, no acceleration. Then as the bar magnet exits the tube, it increases velocity again. So why can't we use a ferrous tube like a steel pipe? A ferrous tube contains iron, meaning that it may become an induced magnet, which would interfere with the falling magnet. So what happens to the magnet as you drop it? So basically, it falls slowly through the tube, and it's much slower than if it was dropped in free space. So what if the resistivity of the conductor were reduced as close as possible to 0? So the braking force is going to increase, which is going to slow the magnet. And if it's fully 0, it's going to prevent the magnet from falling through the tube altogether. So what if holes or slot were cut into the tube? How would this affect the ring currents in your model? So this was going to alter the normal flow of the current through the rings. So basically the braking force is going to be less and not as strong due to this reduced current, which is going to allow the